If you've ever had anything to do with computers, what you know is that the first thing that you come up against is the magnitude of the data that you need to store and process and look at. And indeed, Professor Andreas Wicenic, that is exactly what he has been doing with the Square Kilometre Array. Did I get the name right?
Almost, yeah.
Almost. So please welcome Dr. Andreas Wicenic.
So first of all, thanks to the organizers for having me here, and I'm absolutely thrilled to give this talk today. Now, the first thing, and please leave the light on. I have black slides but white letters, so you should be able to read it. Anyway, so the first thing I would like to ask all of you is, who knows about the Square Kilometre Array? Oh, that's great. That's great. When I do talks about the Square Kilometre Array in Perth or even in Australia, I've always find that the knowledge about it is fairly low, and that's quite astonishing. But anyway, let's take you through what I have to say here. And I have to say, the talk itself will be maybe a bit less astronomy. The Square Kilometre Array doesn't exist yet, so I can't show you any results for it. But I will show you a few things, what we are supposed to be doing with it. But first of all, I would like to introduce you to the institute I'm actually working at, which is a shared institute between the two big universities, UWA and Curtin University, and has been founded in 2009, especially to prepare Western Australia and Australia to host the Square Kilometre Array and actually get it to here. So just a short introduction. So it was established 2009 as a joint venture between the two big universities here and the state government of Western Australia. So there you see where the interest comes from. Is universities, obviously, because it's research, and it's fundamental research mostly. So what Alan mentioned is definitely true for astronomy. But of course, the state government of WA, the interest is not really the science, be frank with it. It is actually the impact of such a project in WA, and I will talk a little bit about that as well later on. So when we started, we were 13 or 14 people, something like that, all of that. Now we are more than 200. We are the biggest astronomy institution in Australia now. So there you see already the impact, because before almost everything astronomy was over east. That's not the case anymore. So we are more than 200 people now, staff and students, and that is quite astonishing to see growth like that in just a few years, essentially. We got 150 million Australian dollars in direct funding throughout all these years. So in principle, it's not that much per year, especially if you take the 200 people there. But in addition to that, we've actually won about more than $100 million in competitive grants. So for the universities, because they're only a quarter of all that money is coming from them directly, it's about a 4-to-1 factor. When they invest their money into us, they get $4 back in research funding, which is great, or from the Western Australian government, which is great for them. In the meantime, we are ranked at the top 5 centers in radio astronomy in the world, which is quite a privilege, but it's also a bit of a burden in a way. And we are looking into getting, we had quite a number of pre-construction contracts for the SKA, and that was all funded by the federal government. ICRA consists of 3 big programs, and one is science, the other one is engineering, and the third one is data science. Now, I'm leading the data science part, so bear with me. I'm not talking too much about science, although I'm astronomer in background. But we are doing a lot of science, actually, and we have many, many papers in the meantime, about 1,000 papers. from just ICRA. And here are a few examples. So we just heard about the Magellan Clouds. There you go. There's a very detailed study about them. And we have a few people at Curtin working on black holes as well, and neutron stars, and how they form and how they interact with the environment, their environment. We have actually quite a number of people working with optical astronomy as well, although we call it radio astronomy center, but we do optical astronomy as well. Simon Driver and his team working with all kinds of observatories around the world, including some in space. In this case, the Hubble Space Telescope. And then the late J.P. Marquardt, and unfortunately he died very suddenly last year, but he was one of our brilliant scientists, and he used the Australian Square Kilometre Array Pathfinder to do very, very exciting stuff, which is also something which we will do for the SK. I will talk about that later. And then in terms of data science, so we are doing a lot of stuff in data science, trying to enable science which we can't do right now because we just have too much data. And we have a very big team in the meantime doing a lot of cosmological simulations. You have seen that actually in the almost, I think, the last slide from the last speaker. This web of the cosmos in the background. So if you look at a very large scale, you see these filaments going around, and that's what these cosmological studies are doing, trying to figure out how that looks like. Mostly in our Curtin part of the institution, we have a lot of engineering going on, and that's in preparation for the SK, but also to actually run one of the telescopes. I will come back to that later. And they are designing antennas and receivers and the way they would work and test them out and put them on the ground, actually. So both of these images are actually real images of stuff which is currently sitting out there in the Murchison Shire in Western Australia. And one is called the EDA2, AAVS1. Forget about the acronyms. We have so many. I won't take you through all of them. It doesn't make too much sense. So it's low-frequency antennas which are sitting on the ground. So some of them are just that big. The other one's a bit bigger. And we are trying to have the best design for them. And that's what they are trying to do. This is an extremely harsh environment out there. Temperatures go up more than 50 degrees in summer. Very, very harsh thunderstorms as well. It's just raining quite heavily every now and then. So it's really hard to get stuff done out there. But that's where we want to put the SK as well. So these two images are showing how we are simulating antennas, how the antennas are actually reacting to signals. So that's done a lot. And then we do another piece of engineering, which is the timing system for the SK mid telescope, which will be built in South Africa. The last part, data-intensive astronomy, I'm heading that up, and we are using the biggest computers in the world, and I will describe that a little bit more in detail, what we've done there. We are collaborating with quite some companies, the biggest ones in the world, but also very small ones, startups around here in Perth and also in some other places. And we roll that out, so the thing in the left there, that's actually a piece which is being used for the Murchison Wide Field Array, which is operational already. And then we do computer programming. So, of course, these computers are not just sitting there churning a lot of power. They actually run programs. And we do that, algorithmic development and trying to get the best out of it. Now, astronomy is good and fine, but we are doing a bit more than that. With all this expertise and knowledge, we actually do ocean waves as well, like these swells here. And that's quite interesting. So we are doing swell prediction for the oil and gas industry. And we do some things with honeybees, honey, Can you imagine that? It's totally different, right? What has that to do with astronomy? But data science is very generic, so we actually use that expertise to do totally different things as well. One big thing is communication and outreach. Now, astronomy is very fortunate. I mean, if you heard the last talk, that's just marvelous, right? You can show all these pictures. Everybody's interested anyway. So we only have to add dinosaurs, which we did today, and then we have everybody in the room. It's easy. It's just easy. So we do a lot communication and outreach, and our small little department is actually extremely active and very successful as well. So we have reached about 250,000 people directly with that outreach team during the last 10 years or so. And that's quite astonishing. And that's schools and Astrofest. Who had been at Astrofest? Nobody? Few? Okay. So Astrofest is actually the biggest astronomical event in the southern hemisphere, which is quite astonishing. It's happening every single year at Curtin Oval. And we have lots of telescopes there, and Perth Observatory is helping us there. It's quite something. About 3,000 to 5,000 people coming every year, and watching the night sky and having a good time. Lots of talks as well, and presentations and booths and so on. So it's a really nice event. It's usually in March or so every year. So ICRA has a 5-year life cycle essentially. So every 5 years we have to get more money or see how we survive. And this was the last time when we brought it up. And what you can see there is actually we tune the whole tone into something which is actually impact of that project to Western Australia and Australia in general. So that's the title of this whole thing. We had been, and that was actually a mandate from the state government, we had to have a review of the whole thing, and that's an impact study of ICRA onto the state. So Deloitte Access Economics did that for us, and that's quite successful for us. Now, let's go to the SK. You're interested in SK, so I will talk about the SK. ICRA, as you have seen, is very tightly related to the project, and indeed we had been working on that for all these 10 years to get there. Now, what are we going to build? It's 2 telescopes, not just one. There's 2 big things. The upper one will be in South Africa, in the Karoo, kind of semi-desert area. 200 of those dishes distributed across 200 kilometers approximately. And in Western Australia, it's this absolutely enormous thing. 131,000 of these antennas in 512 stations, 256 each. And those are about 2 meters high. So look like Christmas trees, pretty much. And we have a few of them, and we are using them as Christmas trees around Christmas time. We put our stuff here. It's actually pretty funny. But yeah, that's our antennas. And we will have a lot of them in Western Australia. So the 2 places is, as I said, South Africa, and you see the bright spots there, and Western Australia. But what we are talking about right now is SK Phase 1. SK Phase 2 is far bigger than that. It's going out over a good part of the African continent, and probably will spend quite a bit of Australia. Maybe not as far as what's here, because this slide is pretty old already. But depending on how much money we can get, we can make it bigger. But these are just stations, so don't see that as single antennas. Especially in Western Australia, it's a lot of antennas in one spot. So what are we going to observe? It's 2 main things. First of all, this is radio. So when you think about radio, you think about your FM radio in your car or so. Not a lot of people are using that anymore, I think. But anyway, so you have those radios, and what is going to be built in Western Australia is essentially FM band. It's 50 to 350 megahertz. So it's a bit on the lower side and a bit on the higher side, but that's where it is. And that's the main reason why we don't want to be anywhere close to people. Just no. This is disturbing like crazy, so we don't want to do that. And that's the main reason why we are way out there in Western Australia. The mid-frequency array starts from 350 megahertz, just at the upper bound of the low frequency, and goes up to 14 gigahertz. Now, somewhere in between, there are all kinds of crazy things, like stupid mobile phones, and all the satellites supporting them. So that's pretty covered. So we have to make sure that we can actually get good observations out of that. Now, apart from the frequency range, we are also looking into the time domain. Now, we heard about gravitational waves and nice little black holes coalescing and stuff like that. That's this domain. Transient universe is really in. So if we want to observe something, it has to blast, and that gives us good outreach opportunity as well, obviously. So we will try to get transients, things which blip up in the sky, between 800 microseconds and about 10 years. So whatever you can find there. And that's variability more than really transients. We do have a few things in Australia and also across in China already, which are officially called precursors. One is the Australian SK Square Kilometre Array Pathfinder. That's the one in the top left there. It's a mid-frequency dish array, 36 dishes with a very interesting receiver technology. The one in the middle is the Murchison-Whitefield array, which is really low-frequency thing, like the SK will be here in Western Australia. And the one in the far right there, that's a monster. It's 500 meters in diameter. It's built in China Southwest, and it's just absolutely amazing when you see it. I had the pleasure to be there and see it, and oh God, what is this? It's amazing. It's absolutely amazing. And we are a little bit involved in that, but this is a Chinese instrument. So where we are with those precursors, both MWA and ASCAP, are actually in the Shire of Murchison. This Shire, it's the size of the Netherlands, and there are 120 people living there, registered there. The population density is 1 toe per square kilometer. That's what that number means. So there's nobody there. It's great for us. Actually, most of these people are not really permanently living there anyway, so that's good for us. So perfect place. It's not too far from civilization, so we can still do something, and that's great. And civilization for us and me is network. And we have seen what happens if network doesn't work. You can't even look at a YouTube video. What is that? Okay, so we have actually a network between that site, which is a nice little red thing there. These are the ASCAP antennas, and up there on the right there's the computing center. The first stage of computing is just there. And that's inside that. There are lots of racks, lots of computers, lots of stuff there, and lots of networking. So we can't do that wirelessly, and we don't want to because it would disturb us ourselves. So we don't do that. And we have a network which is going all the way down from there through Geraldton and then up down to here at the Policy Center, and we have a 800-kilometer dedicated network to do that. Of course, why do we do the SK? Well, it's science, and that's why we've pushed it forward. So let's start with the science. So these are real images, obviously not taken with the SK. The SK could do that much better, about 100 times better than what you can see there, and much faster. So this took actually pretty long to take. Radio astronomy is very complex to get data out of it. But it's not only the radio part, which you can see there. The radio thing is the orange part. All the rest is the optical background. Now, if you look at the center, there's this bright object. That's what you actually can see in optical. You can't see any of the orange stuff when you look at that object, but it's all connected. So this small little galaxy is actually a huge galaxy in reality, but it's much, much bigger on radio. And if you want to understand what's going on there, you have to know that stuff as well. Else you don't understand the whole thing. Now this is a simulation coming out of a computer, a very big computer, to say the least. It's a simulation of the cosmic web. That's how it's called. And what it's showing is actually not galaxies, it's showing only gas in this case. So you have these gas things going around in these filaments. And in the knots of those, that's where gas is clumping. That's where you have galaxy clusters, not just single galaxies, it's whole clusters of galaxies. And that's what our colleagues are doing in the cosmological simulations. So this is just 2 glimpses of science. The SK Science book is a 2-volume thing. It's monster, 2,000 pages. And it's science ideas ranging from the very solar system around here, observing Jupiter with the SK or something like that, and of course the sun, and to the very early universe. Now the low frequency part of that instrument, which is going to be here in Worcestershire, is actually mostly about the very early universe. So it's just a glimpse of the main science drivers. So we have the galaxy evolution and cosmology and dark energy as well. So there you go, you have dark energy. Of course, as David said, we don't know anything about it in reality. So hopefully we can shed some light on that. Then gravity using pulsars, that's quite interesting use case, and a lot of effort went into that. I won't talk about the details of that. That would be a total talk by itself, and I shouldn't really talk about it because I have no clue about how it's working. And then the origin and evolution of magnetism, which is very badly explored, although it's one of the big things in the universe. Magnetism is very important. We heard that last talk as well. The aurora is, of course, guided by magnetism, in this case the Earth magnetic field, but all the objects in the universe actually have a magnetic field, so, or most of them at least, and some of them very strong. And then the probing of the cosmic dawn, that is essentially the low frequency array focus. That's what we are trying to do. And remember that picture. I will show something similar at the end of the talk as well. And then the cradle of life, that's a bit, you have to mention that for the SK is a bit far-fetched, but we can do some things in there as well. And that's going to be complementary to other observations. And one thing which is pretty unique for the SK is in the main science goals, we have this exploration of the unknown. It's just written in there. And the reason for that is because the SK is a quantum leap almost into the next generation of instruments, because we are about, in some areas, about a factor of 10,000 better than what we have right now. Some other factors only a factor of 100 or so, but whatever number you take, it's a lot. And if you're observing something like that, of course you will see things you have never seen before, and that's what this theme is about. And why do we do it at all? Why is WA or Australia interested in this? This is about impact, really. So this graph shows our, and only up to 2014, how many collaborations we have put together worldwide from the center into the world in all of these collaborations. We have about 350 people coming through, COVID allowing, not now, of course, every single year, visiting us for sometimes an extended amount of time and doing science with, together with them. So it's a long list of institutions and also companies in this. Education and outreach, we had that with David. And of course, that's very important. SK is a 50-year time span instrument. So obviously, we need to have young people coming into this. And that's where we definitely have to do a lot of work, and we do a lot of work to get young people interested into STEM in general. And of course, innovation. Wireless has been mentioned, so that came out of radio astronomy. Great. We probably won't be able to do something like that again. Maybe, who knows? But there are other things. So what you see up there is an MRI image. Now, that has been mentioned as well. I don't have to talk anymore. I can stop here. Now, the reason why this is relevant is the technology used to produce those images is the same as what we are doing in radio astronomy. Now, when they started doing MRI imaging and so on, they've used actually what we've done in radio astronomy, but now we have to catch up with them because they are much better than us in doing this. The reason for that, there's a lot of money behind that. It's just a huge industry, right? So, so they've done incredible work to get this stuff going, and we have to now learn backwards how to improve our systems as well. This thing down there, I'll mention it later on, that's our work straight away. So the SKA is really an IT telescope. That means it's driven by limitations or whatever we can do with it, it's all based on computers. And that's from the very beginning of when we collect data there at the antennas to the very end when people get their science out of it. So whatever we do, we have to put a lot of effort into it. And a lot of effort means really a lot of effort. So we are using the biggest machines in the world right now just to simulate what we need to be doing. And the last part will actually show that. First of all, how do we get the data from the site to us, and how much is it? So you've seen that already. So this is a 750, 800 kilometer fiber going from the site, and there's a zoom in as well. So from the site to Geraldton, and that's a dedicated fiber, so it has been put in place only for the observatory up there. The part which is coming from Geraldton down to Perth, that's the NBN, and that was the main reason why Geraldton was one of the first places in Australia to have NBN. Was the SKA, essentially. Great. So impact already for every citizen in Geraldton, for sure. So these 400 kilometers were extremely expensive. This is hard rock, it's iron ore mostly. It's just, you can't get anything into the ground. It was an extremely expensive exercise to do this. And it goes to Perth, and it ends up here in this great building. That's the Pawsey Centre. Has anybody seen that? Yeah? Okay. Anybody in there? If you have the chance, have a look into this. This is our version of a small little supercomputer. It's actually really small compared to anything else. But this will host a very big machine at some point. So what we have right now in there is this nice machine, which is on the left there. And the right picture is showing a storage system with tapes, essentially. It's a very nice center. And from there, it goes through the world, into the world. And we have planned already multiple regional centers where the data will end up and where scientists can actually go and do their science. And the same is true for the South African part. I'm talking mostly about the Australian part. Sorry, I'm just ignoring them. Although I'm not. We are working very closely together. It's not like we are competition or anything. It's one observatory, really. So what are we talking about? So we are talking about a lot of data. Now, what you see there is a comparison between MWA ASCAP, so those precursors, and SKA low, and that's just the phase 1. Don't forget there's a phase 2 somewhere at the horizon. And the average speed of the internet, everybody here has probably an internet connection, and 4K video from Netflix. Okay? So the MWA is producing about 12,000 megabits a second. As we speak now, it's doing that, right? So it's just pumping out data like crazy. That's about 150 times your average internet speed. I've looked that number up yesterday, so it's pretty close, 80 megabits a second approximately. That's what people have in their households. I don't have that. I don't want to pay that in reality. So, no, thank you. But anyways, a lot of people seem to have that. That's fine. And that's 800 4K Netflix videos in parallel going out. That's nice. ASCAP is a bit bigger than that. It's already almost 300 times the average internet speed, and 1,500 of these videos running in parallel. Now the SK1 low is just astonishing. 3 million megabits a second, and 3,000 times, or almost 4,000 times the speed of average internet. So it's a huge jump in terms of how we deal with that data. And that's one of the main challenges, of course. And it's not just that we have to be able to transport it, we have to process it as well, else no science will come out of it. So processing is the key of it. Now the way we are tackling that, and that's the way the computing world is going, every single laptop, every single phone even, has more than one computer in there. So the chips which are doing the computations are actually multiple cores, that's how it's called. So it's many cores and not just one. So it's small little computers bundled together. Now we go a bit bigger than that, but it's the same principle. You just split it up into many computers and start from there. So the parallelism you have seen on this domino thing, that's exactly what we are doing. We use that, run the data in parallel through many computers, and try to get something out of that. But it requires the biggest machines in the world to do that scale. And we tried that in 2019 actually, and selected as one of the finalists of the Gordon Bell Prize, which is kind of a Nobel Prize in high performance computing. That's what people are saying anyway. So it's an extreme achievement to be able to even do that, to try to do it, rather than doing it in reality. We didn't do it in reality, so but we ran all this mechanism in parallel on 27,000 of the best GPUs in the world. The processing power is absolutely astonishing. At that point, that was the biggest machine in the world. So I have this video, and I will leave it running in the background. There's some nice music as well. I won't actually go there. So that's where the computer is actually located in the US. And it's still there. It's called Summit. And it consists of 256 cabinets, 2.4 meters high, with a lot of computers in there. Altogether, it's 4,600 computers in all of these racks. And we've used all of them to simulate the 131,000 antennas of the SKA, then take that data through our ingest pipeline, what's the first stage of the processing, so the GPUs actually are generating the data. There are 6 of them on each of those computers, and we take the data out of them, averaging them down, which is what we will do for the very early universe observations, and again an averaging step, and then we put them on a file, and then we pick up that file, or it's actually many files, and produce the input data out of that again. So we just take that data and see whether we can reproduce what we put in the first place, because we've simulated it, so we have to be able to essentially get the same out again if we want to be successful. And that's what we've done. So you see all these 256 cabinets here, and then we have a system which we call Daluji, which was actually distributing all this processing onto all these machines, getting all the data out, and then producing the input data again, which is this what we call a data cube. So it's images, planes, one after the other. In this case, 356, I think. And that's spanning the first few 100 million years of the universe. That's what we put in the first place. So there you go. Now we are going through that cube plane by plane, and every plane is essentially a certain time slice of the universe after the Big Bang. Okay, and what you see there is the first stars and galaxies forming. And at the end of this whole thing, it's black. And that's what we see right now, right? So if you look at the sky, it's mostly black. And that's what you would like to have. Now, in the beginning, it wasn't black. It was actually not transparent at all. You couldn't see anything because the material was not ionized. And the first stars and galaxies did ionize that. Now, where are we with the SK? So my few last slides, bear with me. The construction plan has just been approved last month, end of last month. So this is a highly complex international project. There are 15 countries now involved and a few associate countries as well. So this takes all the governments to align with each other and say, oh, we are giving you so and so much money and so on. It took forever to get there. Now we are at construction. Officially, since 1st of July, which is only a few days ago, we are in construction rather than pre-construction. So suddenly the whole thing gets kind of real, and hopefully in a few years we have real stuff on the ground. And of course, now the feedback comes. So ICRA and quite a number of other institutions and also companies are currently applying for construction contracts. And we are in a good position, with a bit of fighting to get there, to have a sole source contract, which is interesting. So we are bidding for something which only we can get. Great, isn't it? So, but that's the current situation. Hopefully we can sign that within a few weeks from now, and then we can go truly into construction and do the work we were supposed to be doing and get this thing on the ground. And for us, it's mostly to get the computing going. So this is the timeline. Maybe you can't read it. So it goes down to July 2029. That's the last line there, end of construction. And this is SK phase 1, okay? Always remember that. So it's still a number of years in the future. But radio astronomy is actually very nice because you can start observing very early on. You just put a few antennas there and you start observing. That's typically not what you're doing because we have those existing ones and they are actually really good. So we don't need to observe very early on, which is good because then it's not disturbing the construction. But we will observe anyhow, just to make sure that we know how the instrument is working, because nobody knows how this thing will work in reality once we have it out there in the Outback. So we will start observing essentially with the first rollout, which is the Array Assembly 1. That's our current target, which is 2025. So that's not that far in the future. And we are trying to get there. Compute resources are simple, easy. We can do that on a few computers. But we want to be ready by the time when we get the real jump. And that's pretty much my talk. There were lots of credits here in the last slide. I may go back just briefly. So lots of things which I collected together and put into this talk. If you have questions, well, either you contact myself or our outreach team, or go to the SK Telescope website, which is great. All kinds of good resources there. And if you are really interested in radio astronomy, there's a brilliant course there from NASA, actually, explaining that. Thank you very much for your attention.
Thank you very much. That was fascinating. The impact of SKA on the West Australian economy, it wasn't just the science and the importance of it, it's the importance of it for our whole lives. Thank you very much.